Hello, everyone. How are you doing? Hope you all are doing well. Today, I'm super excited to bring a new episode of this learning series to y'all. So, this is going to be Python, learning with Python and artificial intelligence, these large language model AIs, particularly Microsoft's and OpenAI's two large companies working together on the ChatGPT4 model within the Bing browser. So today the agenda is to explore AI and human intuition versus reality. We're going to be looking at limitations of intuition in the real world and some context to statistics and nature. Some famous examples where our intuition lacks the alignment with reality. And then we'll also be looking at some coding applications and learning about one particular famous example. Sweet. So, statistics and nature are intuition versus reality. Statistics is part of the mathematical language that models the world. It's very important. It touches every aspect of our lives. Um, my first question that I have is, how is human intuition misaligned with reality in the context of statistics? And I'm going to be exploring that prompt. Um, Yeah. So our brains, as beautiful things as they are, they're not perfect. We have limitations, and we'll be exploring those today with the context of statistics and nature. So one place that I can think of is maybe um, finances. There's a famous phenomena called the gambler's fallacy, and it's where gamblers get stuck in this addictive state where they convince themselves that their odds of winning increase after they've lost. And it's a fallacy. It's just not true. Your odds don't change. In the casino, the person that you're betting against is is a business with a lot of strategy designed for you to lose. And so when you convince yourself that your odds are going to change after you lose, they that's what the casino wants you to think. It's a lie that you have to very caution yourself on, because the odds aren't going to change. In fact, the odds were already against you being in a casino where a big business is working on strategies to um, make you lose money. The casinos operate as businesses to acquire money. So at the end of the day, let's look at this prompt. So, human intuition can sometimes be misaligned with reality in the context of statistics. Nobel laureate Daniel Kahneman theorizes that intuitive thinking has both advantages and disadvantages. It is faster than a rational approach, but more prone to error. He proposed that we have two different thought systems. System one is fast and intuitive. System two is slower and relies on reasoning. The fast system is more prone to error. Would you like more information on this topic? Interestingly, yeah, this is a great idea. So the brain has kind of these two modes of reasoning. It has kind of this lower level mode of reasoning that we do in kind of a fight or flight mode, instinctual, and then there is kind of a higher rationality that we explore. Awesome. So with that in mind, I'm going to copy that here. So what I'm using to document these responses is called Jupyter Notebooks. Um, it's a way that we can organize our ideas for the sake of me making these videos and kind of scripting out an agenda, kind of a lesson plan. Sweet. So uh, it's also within a software suite called Anaconda. I highly recommend it. It's a great place for you exploring AI, especially in the browser, built well into Microsoft Edge. If people want a video on me explaining how I've set up Anaconda on my own machine, feel free to drop in the comments or let me know if that would be helpful. So, with that in mind, we've gotten some context of human intuition misalignment with reality in the context of statistics. So now I'm going to I'm going to ask for some famous examples um, in nature where this misalignment is apparent. And I already mentioned one that I knew of called the gambler's fallacy. Um, But let's see if there's any ideas that the large language model can explore. Um, okay, sweet. So it couldn't find any in nature. Um, so I'm going to ask it about the gambler's fallacy. Um, what about the gambler's fallacy? Is this a misalignment with reasoning and reality? Awesome. So I'm convinced that it is, but let's see what the large language model tells us. Another idea that I'm going to be exploring next is a famous statistics problem exemplifying this discrepancy called um, the three door puzzle or the Monte Hall problem. And so I'll be doing that next, but let's get back to this response. So, yes, the gambler's fallacy is an example of a misalignment between human intuition and reality. The gambler's fallacy is the incorrect belief that if a particular event occurs more frequently than normal during the past, it is less likely to happen in the future, when it has otherwise been established that the probability of such events does not depend what has happened on the past. This fallacy can lead people to make incorrect predictions about future events based on past occurrences. Is there anything else you would like to know? So awesome. This is a great detail of the gambler's fallacy in an abstract approach. So I contextualize the gambler's fallacy based on gambling. The gambler's fallacy is an idea based on gambling in its name. However, it applies to many other modes of life. So notice it abstracts it to past events and making judgments based on past events, even though they're independent. So that was very helpful. I'm going to copy that down here. So the reason why I'm kind of copying this and taking y'all through this is I'm likely going to, for these little lessons and learning that I'm doing with the AI and kind of thought experiments, I'm going to do an open source GitHub repository where anyone else is welcome to access these resources. Awesome. So famous statistics problem exemplifying, right. So I mentioned it before. Three door puzzle is one more example where I'll be exploring kind of this multidisciplinary learning, which I think is helpful with regards to Python and coding being a way that we can furtherly understand or explore more in depth about computationally like quantitative data that can support our claim. So my first question is, what is the three door puzzle and what is the historical background on the title Monte Hall problem? So three door puzzle and Monte Hall problem are they're just aliases. So it's the same. It's the same idea, the same problem. They're just different names for the same thing. So the Monte Hall problem is a brain teaser in the form of a probability puzzle. It is loosely based on the American television game show Let's Make a Deal and named after its original host, Monte Hall. The problem was originally posed and solved in a letter by Stephen Selvin to the American statistician in 1975. In this problem, you are a contestant on a game show and are given the choice of three doors. Behind one door is a car, while behind the other two doors are goats. You pick a door, say door number 1. The host, who knows what is behind each door, opens another door, say door number 3, which has a goat behind it. He then asks if you want to switch your choice to door number 2. The question is whether it is to your advantage to switch your choice or not. The solution to this problem is that it is to your advantage to switch your choice. Under the standard assumptions of the problem, switching doors gives you a 2/3 chance of winning the car, while sticking with your initial choice gives you only a 1/3 chance. Is there anything else you would like to know? Okay, sweet. So basically, this is a problem relating to a huge idea in statistics called conditional probability. So conditional probability is just the idea that you can make uh, a more focused or you can infer more about the probability regarding outcomes in a certain situation if you know external knowledge. So right here you open the door, you pick door number one, and the host uh, the host who knows what is behind each door opens another door which has a goat behind it. So there are two goats and there's one car. He picks one of the doors that has the goat behind it. And with that knowledge, you know that the car is not behind the door the host opens. So it operates on this idea of conditional probability, where you are able to infer more about the outcomes of the events based on external knowledge that you're given. Um, Notice the number of outcomes in the beginning were three. However, by him showing you that there's a goat in the door he opens, there are only two outcomes of the experiment. So you know you could either pick, um, let's say he picks door three, and he shows you that there is a goat in it. Okay, sweet. So if there's two total goats and there's a car, then you know that there's going to be either um, a car. There's two possibilities, right? So there's going to be either a car in door one or door two, and a goat in the other door in each circumstance. Um, so that's pretty cool. So yeah, this is just one example where intuition beats expectation or reality, because or it's there's a discrepancy there because um, many people may think otherwise in terms of that idea. You might not think that your odds change at all once he shows you that there's a goat in one door. Many don't. Um, so let's ask. Actually, can you give some examples? Uh, okay, never mind. Actually, we're gonna be moving on. We're kind of short on time, and this is gonna be running long. And I apologize to be running through this so quickly. There's just a lot to get to, and if you need a pause and digest any of this, that's completely okay as well. Um, One thing I was going to say is this conditional probability also relates to a huge idea in statistics called Bayesian inference, and I highly recommend you look that up on your own time if any of this is interesting to you. Um, but yeah, you will if you go to any of these Wikipedia problems and explore this further, you're going to find more ideas about Bayesian inference. Okay, so that brings us to our last portion of this little learning plan, and that is we're going to be trying to understand uh, how we can contextualize and have multidisciplinary learning with kind of an analytical sense in Python programming. So we're going to ask for a code to model the scenario in Python, and there is a huge idea where you can model experiments in the real world and run them many times to get um, a clear understanding of how how uh, how circumstances and real life phenomenon manifest themselves. I made a video before about the law of large numbers and Gaussian distributions and their importance in our daily lives. Um, I'm not going to talk too much more about that concept now, but it shows up in this Python program that we're going to inspect here in a second. And I encourage you to go watch that video if you're interested in exploring that idea further. But um, so this is the code that we're populated with. It says, sure, here's a simple Python simulation of the Monte Hall problem. You can run to explore the idea further. And then it says the code simulates playing the Monte Hall game and simulation times and calculates the winning probability when switching doors and when not switching doors. You can run the code and see that the winning probability when switching is approximately 2/3, while the winning probability when not switching is approximately 1/3. This should give you more intuition about why switching is the better strategy in the Monte Hall problem. Sweet. So we're gonna actually go ahead and copy this. But one thing is to note is I didn't ask I didn't ask the model to give me comments, and I'm actually going to do that now because this is kind of hard to explain, especially with an audience who might not have too much experience with code. So Let's do that now. Awesome. Could we please get informative comments for what is happening in the code? Sweet. So we're going to explore that idea a little further here. Um, but I'll start running through this with you. So this up here is a package in Python that we import. It's called random. Random is how we can connect our computer programs to model randomness. So we can generate a pseudo random. Notice the term pseudo random means not entirely random, because it's operating on our computer systems that don't necessarily model randomness in the same way that manifests itself in the physical world. It's a model. There are limitations of a model. There are always limitations of a model. So you just have to think about that as well. Um, Sweet. So it's writing the code with the comments, and I'm going to continue running through this now with y'all. So we first make a function called Monte Hall. Monte Hall was the talk show host who opens the door and shows a goat. Um, Sweet. So and it takes in a parameter switch. Switch is basically going to be a binary decision if we're switching our door or not switching the door after he's shown us one of the doors with the goats. And so doors is just an array or a list of 1, 2, and 3. Car is going to have a random choice of doors. So we're going to pick a random choice of these doors. So that's what the car is going to be behind. Then we're gonna have our choice, right? And then we're gonna remove our choice from the selections. Um, and then if the first choice that we had was the car, um, we're gonna we're gonna then be there's gonna be a new variable called reveal defined, and that is gonna be uh, one of the doors. So this is the host essentially revealing that the goat is behind one of the other doors, and so we're gonna reveal one of those doors, uh, right? So the host has to reveal one of the other doors, and then we're gonna remove it. And if the first choice is not the car, then we're gonna remove car from the doors as well. And then we're going to have reveal be the other selection. And the reason why why we're removing, so what's the discrepancy here is the way that we select the door, right? So we're just selecting the door in a different way based on if our first choice is the car or not the car. And that's just the talk show host revealing the goat. And then the contestant makes their first choice. So if we're switching, then this is a little bit of complicated code, and this is called list comprehensions, I believe, in Python. Um, and so, like, if you got tripped up on this, you could grab the code and be like, I want to understand this more, but it's a little bit confusing to me. So door for door in 1, 2, and 3. If door not is in the first choice, reveal. Like, I'm not gonna lie, I have never seen a person write code like this. This is definitely very obscured and kind of confusing. So I'm not definitely content with the way the AI does this. And then I'm gonna look at that's the first. Okay, so this is basically making the final choice, right? Sweet. So this is the final choice that we select. And then if our final choice is the car, we're going to return a binary outcome. So this operator is basically saying if our choice is the actual door where the car is, then it's going to return 1. Otherwise, it's going to return 0. And why that's important is because when we're running these simulations, so we're gonna run the Monte Carlo, sorry, not Monte Carlo, Monte Hall problem 10,000 times, and then we're gonna see if we win when switching or if we don't. and then we're going to get the probability of each event. So we're going to actually run this now. So I'm going to copy this, and we're going to see if we get the same result as explained. So we should see that when you switch, you have a higher a higher chance of winning, about 2/3. And when you don't switch, you should see that the probability of winning is lower, at about 1/3. Whoops, I didn't take this comment out. My apologies. Looks like there's some stuff up here didn't take out. And so, awesome. So we were able to analytically verify this problem in code. I know this video is probably running a little long, so I'm going to cut it off there. I just wanted to let y'all know. Thank you for tuning in. If there's any other ideas you would like me to explore, or feedback that you have, I would be highly appreciative of it. Have a wonderful rest of your day. Thank you.